Okay, thank you very much. Thank you to all the participants for attending the workshop. It's my pleasure to introduce Professor Niyaz Tokmagambetov from Ghent University, who will talk about non-harmonic analysis of boundary value problems. So Niyaz, you have 45 minutes plus 5 minutes of questions. Thank you for accepting our invitation.
Hello, everyone. Thank you very much for organizers. Thank you very much, Duvan. I would like, today I would like to talk about non-harmonic analysis of boundary value problems. This work actually was started with Professor Różański in 2015. We will talk here about some introduction and some model operators which will generate our analysis, and about theoretical part of global distributions, test functions, and other stuffs that we need to develop theory of pseudo-differential operators. So here we actually develop the global symbolic calculus, this calculus is somehow connected with non-self-adjoint operators, and of course, as a result, we will have a non-self-adjoint distribution theory and corresponding some b-orthogonal Fourier analysis. And the application part is also huge. At least we will talk about some a priori estimates for solutions of boundary value problems. And the main topic of this talk is related is from the paper with Professor Różański, which is published in 2016. And indeed, we know different powerful approaches just to study boundary value problems. We have already developed a series by Monvel, by Mazias Hall, and Melrose Schulz, and actually, indeed, the list is much more wider than is given here. We mention here only several persons, and our approach actually is different from all this, just being somehow globally, and as the starting point, we started from developed from the toroidal calculus. Calculus on torus first was done by Agronovich, in the 70s, and later there are a list of people. They developed some different properties, and the developing calculus on torus was started actually is very powerful, and we have a lot of techniques in that area, and also some guys developed these techniques to upgraded to the groups and more symmetric structures. But in this paper, we developed our approach for somehow for non-symmetric structures. We started from the generating operator, and we actually assume that omega is just some bounded domain, and on bounded domain there are a lot of differential operators can be defined, and there are a lot of classes of operators on bounded domains, which has a discrete spectrum, and the eigenfunctions and eigenvalues, and these things actually our blocks for developing our calculus here. Just by L we will develop some model operator. Just in general we will use only some properties of its spectrum or eigenfunctions, and also we will use conjugate operator. Just L star is conjugate operator. There are some technical assumptions on eigenfunctions. So u, v, u psi is eigenfunctions of our L operator, and v psi is eigenfunction, the system of eigenfunctions of conjugate operator, and from the Barry's work we know some we can say some elementary properties, and we will assume in this work just basis properties, bi-orthogonal basis properties of our systems. As examples, so we try here give some elementary examples. Just let's say that O operator O is just differentiation operator is given by the formula, by this formula, with some boundary conditions on the domain omega, which is a 0, 1, interval 0, 1. And here, when h is equal to 1, we get some periodic boundary conditions. And then we can talk about the problem developed on torus, but in general, even in here, we can see that our approach is much more powerful, much more just maybe structurally different, even from torus case. So of course we are not. We also we cannot concentrate on boundary conditions. So in general, we can have look on the boundary conditions with some integral terms, and this kind of properties also they could have problems with this boundary conditions. Also they have spectral discrete spectrum, and the eigenfunctions forms. System of eigenfunctions forms basis in L2, and there are plenty of properties also exist. These problems initially, for example, Professor Convolution and Nurahmetov, they studied this kind of problems, and we first define the space of test functions. So by CL, we will denote the space of test functions. So we define this test function just like a domain of the operator infinity, just by iteration, but just as here, where just domain LK is the domain of the operator LK, just K times iterated operator. Also, the interesting case, just in our calculus, we have test functions of generated by the conjugate operator. It's also can be introduced in the same way, but instead of operator L, you can take just L star conjugate operator, and from just using the simple from the duality formula 4, yeah, we can develop we can define class of distributions dl prime as a space of which is a dual to the conjugate test functions. Just like this. And by S, we denote the space of rapidly decaying functions, just somehow this structure may be very close to the one toroidal one that introducing, but here we have always we should think about the conjugate and over space generated by conjugate operator and by original operator L or model operator L. So now we define L Fourier transform and L star Fourier transform by using formula 5 and by 6. So this kind of transforms can be just actually they are Fourier coefficients. They can be you may think that they are coefficients, Fourier coefficients, but just generated by the system of eigenfunctions Vxi and the Uxi. And here we have some nice properties, just saying that the L Fourier transform is a bijective homomorphism from between these spaces. And we have nice inverse formula for the transform, for our Fourier transform, and also we can extend our Fourier transform distributions. And also we have L star conjugate case of the Fourier transform. And again, we can do the same with them, just define on the distributions. So for the convolution, convolutions are also one of the main stuffs in calculus, and just defining in this way just can be explained later, but what can be calculated that in the torus case, this convolution would coincide with the toroidal one, just in distributions, just in the space of distributions. Just again, we have not just one convolution, we have two convolutions, yeah, just generated by operator L and the L star. Yeah, we here somehow tried to calculate kernel of the convolution, and just in the torus case, we actually found that they are somehow related to the classical one. And okay, just the main property of the convolutions in our calculus is just stated in the theorem. And okay, we now can introduce Sobolev spaces, just Sobolev space of sequences. Just in this way, again, we have some analog of just analog of Plancherl identity, and just introduce original Sobolev space itself in terms of our calculus. Again, our Sobolev space are generated by operator L, and also we have some siblings of the space, just L generated Sobolev space generated by L star. There are some relation, just some formulas on it, just and also we can introduce some LP, the space of sequences LP generated by L and the L star also. We choose it. Just when we choose this kind of spaces, there was several ways to define these spaces, and we adapted actually these spaces just to have nice formulas for the Hausdorff-Young inequality. So now we have analog of Hausdorff-Young inequality and some duality properties also. And now it's a way to introduce L symbols of operators on omega. Just okay, just we just for L symbol can be defined for any linear operator. Just let's say that we have linear operator acting on this space between these spaces, and for that space we define by Fourier transform and by kernel of the operator we define symbol L symbol. And for the convolution kernel, we also can be regained from the symbol by formula 15. And here some L quantization theorem that any operator, linear operator, continuous linear operator with symbol with L symbol can be defined by formula 16. Can be quantized by formula 16 with the symbol 17. And so here we give some equivalent formulas for L symbols. And actually here in our paper we use it so-called WZ condition on eigenfunctions just without zero. But later in our paper with Michael we just relaxed this condition just so we may think about we may not think about the zeros of eigenfunctions. So because technically it's the class of the operators L is very narrow, just to satisfy the condition WZ, and it's and why we just studied that case separately and tried to relax that conditions. And for we also have formula for difference operators. Yeah, they usually written by huge formulas, but ideas are simple. So what is interesting in our calculus? Just we observe that our difference operator depend on X also. So in the classical case, they usually do not depend on space parameter, but in our case, so we observe that it should be. So again, we have some second pair of the difference operator, and now we can define simple classes, as in simple classes. L star symbol classes, and some definition. So we can define L pseudo differential operators. And some formulas for adjoint operator. Just if you know symbol, if we know some information about the operator A, and just it's about its symbol, we can calculate symbol of conjugate operator to A. And some composition formulas, just it's one of the main ingredients to develop one main ingredients for our calculus. So okay, have some integral kernels. And I think the more interesting things can be found in our paper. Just with we have some results on this. So we have some analogs of Sobolev embedding theorems, L2 boundedness, and so on. And I also want to mention that recently with our colleagues, with Duvan and Vishvesh, we started just to develop further properties of the L pseudo-differential operators. So in particular, some LP-LQ boundedness theorems are proved by our group. So thank you very much.
Okay, Niyaz, thank you very much for your talk. You are open for questions now. Someone has a question for Niyaz? I have a question, but myself, you show one-dimensional example, yes? Have you also dimensions of arbitrary examples of arbitrary dimension, yes? For this kind of models operators, yes?
Yeah, sure. Just maybe here, just for simplicity, we just only give some one-dimensional cases, but in general, we can think about the Laplacian operator, some defined on some bounded domain with some Dirichlet boundary condition or so on.
Okay, for this calculus, you also developed the Schwarz-Kernel theorem, yes? That was for this calculus, you also developed the Schwarz-Kernel theorem, yes?
Yeah.
That was a central tool for.
Yeah.
This was unknown for the harmonic analysis of this, for this anharmonic analysis before, yes? That was new result, I mean, this kind of Schwarz-Kernel theorem, yes? You show here the case of domains, but also you have generalizations to manifolds, yes, with boundary and with more structures.
But, yeah, with Julia, we develop also with Julia. We have some with Professor Różański, with Julia, we have developed calculus on some on manifolds with boundaries, yeah. But it's a more general case than one-dimensional case.
Okay. I have another question, probably with the structure of the difference operator. You mentioned that in the case of company groups and so, the difference operator does not depend of the spatial variable, but in this case, difference operator depends on edge. Yes, this is one of the main difference. Yes, with this calculus of.
Yeah.
Yes, in this formula. From where you get the inspiration for considering these difference operators, but associated to this function Q alpha, but here Q alpha is defined in two variables, in X and Y. Yes, from where you took this, because in the case of company groups, this Q function is only defined on the group, only dependent on X, but here Q depends on two variables. Yes, from where you took this inspiration.
Unfortunately, we didn't give some definitions on Q. Yeah, but
yes,
they usually satisfy some conditions and existence of such functions. We don't care about the explicit formulas for Q, and actually Q could be class for Q is wide. So there are plenty of functions just that can be taken as a main, to generate these difference operators.
Okay. More questions for Niyaz? If not, so thank you very much, Niyaz, for your very nice talk. This indeed is a topic of with many open problems. If someone is interested, can ask to Niyaz, can email him. Okay, so probably we can close the workshop.
Yes, just to finish, have some small comments. just to close the conference. Maybe, I don't know if Larry and Duan want to say something, but okay. So, are you watching my screen? Oh, my computer got freeze, I think.
Yes, we can't see your screen, yes.
Can you see my screen? Okay.
Now, yes.
So just we wanted to remind you that the idea of this workshop was to people from both groups, from Professor Sikar-Zelinsky and Professor Rusansky, know each other works, interest, so that in the future we can collaborate together to make really nice research. So this online workshop has like that many purpose. Of course, maybe online is not enough. So I think in the future, there are some plans to maybe try to do it in person, in London or in Ghent. But anyhow, if some of the talks got your attention, please, I encourage you to contact the speaker so that maybe you can have further discussions in that direction. And yes, I wanted to remind you that, and also just to close, I want to, of course, thank you, all of you, for attending the workshop. Of course, thanks the speakers for such nice talks. Thanks Professor Sikar-Zelinsky and Professor Rusansky for this opportunity. And thanks, of course, the other co-organizers, Mariana, Duan, and Larry, for such I think good job. So thank you. And I don't know if maybe I don't know if you, Professor Michael Rusansky, you want to say something?
Yes, I can. A couple of words. So I think that this is a good beginning. Indeed, I think that so it's very good that Duan, Santiago, and Larry organize this, and I hope that it will be. I hope it will continue. In fact, maybe in person, and especially well, there is quite substantial groups still. Quite substantial groups, and then of young researchers, and I think it's good to cooperate. This is can be viewed as a first acquaintance in some sense to see what kind of topics. But as you can see, there are intersections because operator theory, log-Sobolev inequalities, analysis of groups. We saw in some geometric analysis, elements of geometric analysis. We saw in presentations from both sides. So I think that it is a very good first step, and I think that it's yeah. So I'm in favor of organizing some events in person. Maybe we can welcome a group from Imperial College London to come to Ghent for a intensive workshop. Maybe we can organize the same way, one day or 2 day intensive workshop, and then maybe our group of people can also go to visit London. So I think needless to say, Imperial College is a nice place, and in the center of London. And when I was working there, many people visited. I think Duan came, right? At that time, Niyaz came, but Wagner came, but there are now new people. Bolas came. But there are now new people, so I think this cooperation can continue, and so yeah. So I once again I thank the organizers for the effort, and for wish a lot of success in the future in organizing further events. So thank you.
Thank you very much for your words, Professor Rusansky, and thank you to all the participants. I think that successfully we can finish the workshop then. Okay, we will upload the talks on YouTube, and then we will share with all of you the corresponding links to the talks. So thank you very much. Thank you, Larry. Thanks to Santiago for the intensive help in these days. So you are welcome. See you.